Now that we've looked at a bunch of different attacks against the app at risk of SQL injection, it's time to start looking at some of the patterns used to defend against these attacks. And in your capacity as an ethical hacker, being able to identify good code versus bad code can be extremely advantageous. Now, the big difference with this module is that we are going to be looking at code. So to identify these risks, we're assuming that you actually have access to code, or you can influence either the way the code is written or the way the app is architected. So this is going to come at things from a different angle. Let's jump in and have a look at what we're going to talk about in this module. So in this module, it's all about understanding where the defenses should be in the code. We've seen what goes wrong when the appropriate defenses aren't there. What should those defenses be? And more importantly, how should the app behave once they're in place? So the goal of this module is to try and help you identify when the defenses are missing. Not just because you've been able to remotely exploit the vulnerability, but because you can look at the code or look at the structure of the app and see where the developer might have gone wrong. Now in this module, we're going to look at a heap of different good practices for building secure apps against the risk of SQL injection. But the idea is to try and apply many of these defenses together. So to take a defense in-depth approach. So what that means is that even though we're going to look at each one of these defenses in isolation, in an ideal system, you'd have many different layers of them together. So they're complementary. If one layer isn't implemented properly, then you have the other layers. There's no single point of failure in the design of the app. And that's a good practice regardless of what it is you're defending against, whether that be SQL injection or other common risks in web apps. But particularly for injection, you'll find that there are a whole bunch of things that should be done in the app, which are often missed. And it's when all of them are missed that we have the problems we've seen in the course so far. So with that said, let's jump into it, and we're going to start by looking at the right way to do error handling. One of the first attacks we looked at in this course was an error-based injection attack. And effectively what we found is that on a page like this one here, we could just simply add one character, just a single quote, and we would get an exception like this. So this is an internal exception bubbling up via the public website. We now know how to use internal exceptions like this to mount an error-based injection attack. But beyond that, it's just unsightly. This is not a friendly user experience either. And it's very, very easy to fix. Now, how easy and just what's required to do it will depend on your technology stack of choice. But let me show you what it entails in an ASP.NET app. Now, we're going to do all this in my local version of the Hack Yourself First website because I want to be able to make changes. I want to be able to secure the vulnerabilities and then show you what the secure implementation looks like. So I'm going to flick back over to Visual Studio, and I'm in the web.config file of this project. So this is the file that configures a bunch of different parameters in the app, including what happens when there's an unhandled exception. Now I'm just going to look for the custom errors section. And we can see down here on line 37 that the custom errors are presently off. Now a custom error effectively overrides that internal exception that we see at the moment. And when we don't have those custom errors enabled, we're going to get those nasty exceptions that leak internal implementation data. So I'm just going to turn this on, save the file, and jump back over to the browser. Now let's just reload this page and we'll see what happens. So this is now a very different exception. There's still an error, and there's still an underlying SQL injection risk, which means that we could still use this resource to mount a union-based SQL injection attack or a blind-based SQL injection attack, but we can no longer mount an error-based SQL injection attack. So an attacker is now not going to see anything explicitly telling them what's going on in the database when an exception occurs. So this one's very simple. And again, be conscious that the implementation will be different in different technology stacks, but implementing proper error handling is normally a very simple thing to do, and it's just good practice regardless of the security advantage it gives you. The next thing I want to look at is really quite pivotal to SQL injection, but also pivotal to other risks such as XSS as well. And it simply comes down to validating untrusted data. So earlier on in the course, we looked at the underlying code, and in particular, the fact that down here on line 16, we're building up this SQL statement, which then gets executed. But the problem here is that when we pass in this cylinders parameter, so this is the one that comes from the query string, we're never doing any sort of validation on it. So what do I mean by validation? Well, let me give you an example. One way would be to use the code I've got on my clipboard here. I'm just going to paste that in. And this is a whitelist of allowable values. So what it's saying is that our allowable cylinders can be V6, V8, and so on and so forth. And if we don't see one of those values in that cylinders parameter, we're going to get line 20. So it's going to throw an exception, invalid cylinder value provided. I'm just going to recompile this solution, and then we'll jump back into the browser and we'll see how the app behaves now. So the first thing is we'll make sure the page still loads okay, which it will because V12 is one of our whitelisted items. But if we were to make a change, even such as adding a single quote to the parameter, let's see what happens. Okay, invalid cylinder value provided. Now per the last clip, you never want to actually show this underlying exception, and inevitably you'd handle this more gracefully. But you can see the point. Now you do have to be a little bit careful with whitelists, because it also means that something like this won't work. What if we had a V5 engine? It's a valid engine layout, but we have an exception. Invalid cylinder value provided again. So you've got to be a little bit careful with being explicit. There are cases where it works well, where you only ever have a known set of values, but it doesn't work as well when you need to look for patterns. So let's jump back into Visual Studio and I'll show you what a pattern might look like. Okay, let's replace the code I had here just before, the whitelist, and instead I'm going to use a regular expression. And this regular expression says that the cylinder pattern must start with a V and then contain digits 0 through 9, and it can have either 1 or 2 digits, and that's it. The string must then be terminated. And if we don't have that, then we're going to get this exception again, invalid cylinder value provided. So let's recompile that and jump back over to the browser again. So here's my test from just before, the V5. Now that didn't pass because V5 wasn't in the whitelist. It should be okay now though. Let's try and reload this and we'll see what we get. Okay, so the page now loads. There are no V5s, which is fine, but the pattern was okay. However, the pattern wouldn't be okay if I did something like this, if I used a lowercase v, because my regular expression was expecting an uppercase. It would also fail if I started having engine layouts like a flat 6. And the reason I'm mentioning this now is that you do have to have a balance in here. You have to try and find the right fit between securing the system and being very explicit about what you will allow versus having a negative impact on usability. Earlier on in the course, I mentioned the number of times websites have blocked single quotes from names, and then anyone who's an O'Reilly or an O'Brien or any other perfectly valid surname gets rejected from the system. That might be secure, but it's no good if a bunch of people can't register anymore. Now finally, both of those patterns I just showed you talked about what we would allow, not what we would disallow. The difference, of course, being the first one is a whitelist and the second one is a blacklist. We always want a whitelist. Be explicit about what we know to be good. Be very, very cautious with blacklisting because you simply don't always know what will be bad. You can make assumptions about it, but new attack vectors are discovered and new exploits may use different characters that aren't on the blacklist. So focus on just restricting these input validations to what is known to be good. One of the things that I've explained multiple times throughout this course is that the database server, when it receives a SQL injection payload from the web app, simply doesn't know that it's SQL injection. And that all comes down to the web app formulating a SQL statement that combines both the query and the untrusted data from the user, such that you can't tell where one ends and the other one begins. So remember, if we have a look down here at the code, down at line 15, where this SQL statement is actually prepared, by the time we get past there, down to line 17 where it's actually executed, even the web app doesn't know what's what. And I want to show you what the database is seeing when we run this query. So what I've done is I've got SQL Server Profiler running on my machine, and that's going to have a look at what the database is seeing. So we're going to jump back over to the web app, reload this page, and now here's SQL Server Profiler. Now there's been a couple of database queries run. I've got the top one selected, and down in the bottom section of the screen we can see the query. Select supercar ID model from supercar where cylinders equals V12. Now let's go to the web app and mount one of our attacks. And we'll just use that simple tautology from before, or 1 equals 1, and then comment out. Let's run that. Jump back over to SQL Profiler. The query is this one just here. Now look at the bottom section where the code actually shows what's been run. You can see what SQL Server is seeing. It's just one clean statement that looks perfectly legitimate. It doesn't know that that single quote after V12 was injected by us. Now the answer to this is really the crux of the answer to all of SQL injection, which is that queries must be parameterized so that the data never actually mixes in with the query itself and changes the logic of it. Let me show you what I mean by that. I'll jump back to Visual Studio, and on my clipboard I have a replacement for lines 15 and 17. Let me paste that in now and you'll see how this changes. So here's what we're seeing. Two things. In the query itself, where we used to just be appending that cylinders string directly into the query, we can now see cylinders equal, and then there's an @ sign P0. And this means parameter 0, the first parameter. We can also see that this is now constant, so it can't actually be changed at runtime. This is hard-coded. This will always be the query. What we're seeing then on line 18, when I actually execute the query using the SQL query method, I'm passing both the query itself and the cylinders from the parameter. And what this method signature actually means is that we're going to have those cylinders passed as a separate parameter to the query. I'll show you what I mean. Let's recompile the application. We'll jump back over to the web app. Now note also we've got every car on the web app at the moment. Let's reload the page. Now the first thing you'll see here with the page reloaded is that there are no cars whatsoever. Let's jump over to SQL Profiler and see what query the database actually saw. So the query that we're after will be this one just here. Now have a look at the statement down the bottom of the screen. This looks quite fundamentally different to the earlier one up here. So see, this looks like just one simple SQL string. The new one down here, the parameterized one, actually passes V12 as P0. So in fact, if you have a look at this segment of the query, this is what we had hard-coded into the app with the update I just pasted in. You can see the @P0 there at the end of the highlighted section. And then you see as a separate parameter in this sp_execute SQL command, P0 is declared as an nvarchar 13, and then the value of it is actually our SQL injection attack. So it's V12 and the quote and everything after it. And in fact, you can see that even the quote has been escaped. We've got two quotes after V12. So effectively what this all means is SQL Server is now doing what it really should do, is that it's taking the entire parameter, so the actual SQL injection attack, and it's looking for supercars with cylinders that match that. Which of course they won't, because we don't have any cylinder layouts that are a legitimate SQL injection attack. So this is critical. This is the heart of the fix for SQL injection. SQL command parameterization. Get this right and injection simply stops. You simply cannot break out of the data context and into the query context. Now this isn't the only way of doing this though. Let's move on and take a quick look at how we do this with a stored procedure. Stored procedures are another really popular way of implementing queries against database servers. And they're also very good at mitigating the risk of SQL injection. Now, stored procedure looks pretty much like what we see just here. We declare a procedure name, and I've called this one Get Supercars by Cylinders. We declare input parameters, and in this case I've got one called cylinders, and it's a varchar 10, so it can only ever be 10 characters long. And then from lines 5 through 7, we can see the query which takes cylinders as a parameter. So very, very simple SQL syntax here. The main thing to note is this at syntax again, where we're passing the cylinders. Let me jump back to the web app and show you what that looks like now. I've just pasted in the code to implement this stored procedure. And there are a few more changes, but the important things I want to point out here include that we've declared the stored procedure here in my new SQL command object. I've created an explicit SQL parameter type, which is named cylinders. It's explicitly typecast as a varchar of 10 characters long. Now that is then added to the parameters of my command. And then the remaining code simply opens a connection and enumerates through and reads the results. So that's the implementation at a code level. Let's jump over to the web app, reload the page, and then we'll take a look at SQL Profiler and see what the underlying query looks like. So here's the web app. It's still showing the result from the last clip where we implemented parameterization, which fixed the SQL injection risk for us. So let's see how the stored procedure approach works. Same end result here, so the old injection risk on that cylinders parameter isn't happening anymore. Let's go and check out SQL Profiler. I'll jump back to the first query here in Profiler, and here we can see what's actually happening. So now we're getting an exec command on our get supercars by cylinder stored procedure. And you can see that cylinders parameter with everything nicely encapsulated in quotes. And just like what we saw when we used a parameter in the last clip, the single quote after V12 has been escaped by another single quote. So those two single quotes together effectively just represent one escaped single quote. So just like parameterization used within an inline SQL statement like we just saw earlier, calling a stored procedure with a parameter keeps segmentation between the query itself and the untrusted data from the user. So stored procedures are another great way of mitigating the risk of SQL injection. Now, one other thing to add here. Some people are of the view that a stored procedure cannot have a SQL injection risk. That's not entirely true. If you're passing a string parameter into a stored procedure, and then within the stored procedure you're concatenating a string and then calling exec, you can still have a SQL injection risk. So imagine if the code that we saw down here was actually a SQL injection payload, and then within that stored procedure, a SQL query was being built up, this untrusted data added to it, and then that resulting string executed. That would still pose a SQL injection risk. Now, it's not a very common practice, but it does happen, and it does show that stored procedures can actually still have the risk. So just be conscious that it's not entirely foolproof. The next defense I want to look at is using object relational mappers, or ORMs as they're commonly known. Now, the beauty of an ORM for software developers is it automates the persistence between entities in the database and entities in the application tier. And it makes querying them extremely simple. So for example, I've replaced the code on the page just here using Entity Framework, which is Microsoft's implementation of an ORM. And what you'll actually see on this page, if we scroll down a little bit, is that there is no more SQL syntax. In fact, the entire query now becomes just one line. So what Entity Framework has done here is it's persisted this supercars model from the database through into the app tier. And we're now using what's called a lambda syntax in order to actually query it. So this is where we're passing cylinders. Now you'll notice here that I'm not doing any specific parameterization. I'm simply asking Entity Framework to get me all the supercars with cylinders that match that parameter that's passed into this page. So let's go and reload the page with our sample injection attack, and we'll see what the underlying query looks like in SQL Profiler. So we've still got the page here from when I tested the stored procedure implementation. Let's give that a reload, jump over to SQL Profiler, and we'll open up the top result here. Now here's the query from our Entity Framework implementation. And one thing you might notice here is that it is actually quite verbose. It's a lot messier than our parameterized inline SQL or our stored procedure call. In fact, it's even got a nested SQL statement. Now there's an entirely different discussion around the efficiency of SQL that's generated by ORMs. But the really important point here is that you can still see that that v12 followed by the injection attack is passed as a parameter. So the parameter syntax is actually the same as what we saw earlier on with the inline SQL implementation. The beauty of ORMs like Entity Framework is that they automate parameterization. The developer need not know anything about parameterization, although I strongly suggest they should, and the framework automatically takes care of it for them. So using an ORM is very much falling into the pit of success. It is set up to avoid SQL injection in the first place. That's just simply the design of them. But like stored procedures, they're not entirely foolproof. You can still build up a SQL string with untrusted user data, simply concatenate it into it, and then execute that against the data context of an ORM like Entity Framework. In fact, that's how I did the original bad code that we've been exploiting throughout this course. So just using ORMs alone doesn't mean you can't have an injection risk. But using ORMs in the way that they're designed to be used means that you end up with queries like this, automatic parameterization. So that's ORMs, and that wraps up the three different types of parameterization I wanted to cover. Inline SQL with parameters, stored procedures, and then of course the object relational mappers. Let's now move on and start to look at how we can actually tackle this from the database side using the principle of least privilege. So far on defenses, we've only looked at the web app. So how can we keep our errors from disclosing internal implementation details? How can we reject invalid, untrusted user data? And then how can we parameterize using inline SQL parameters, stored procedures, or ORMs? I want to take a look now at the database layer itself, and particularly at the principle of least privilege. And this is a really fundamental concept, not just with database permissions, but really with any part of application design. And it's all about identifying the bare minimum permissions that each component of the system actually needs to do its job. And inevitably, what we have at the moment, and something that I've mentioned many times throughout this course, is that the web application is connecting using an identity that's got far more access rights than what it actually needs. We particularly saw that when it came to access rights that allowed the web app to do things like create SQL logins. That should never be able to happen. There's absolutely no reason why an anonymous user browsing around a public website should actually be talking to the database with enough rights to escalate their own privileges by creating their own login. That's just a ridiculous situation to be in. So let's jump over to SQL Server Management Studio. And in my Hack Yourself First database, we can see that I have a user called Hack Yourself First Restricted. Now, this is exactly the same as the account that's used on the live public website. Let's have a look at the permissions that this guy has. If we go into Properties, and we have a look at the memberships of this user, it's a member of both Data Reader and Data Writer. And that means that by default, it can read and write from any single table in the database. Now that's excessive. We don't need to be able to do that everywhere. So as an example of the principle of least privilege, let's remove both Data Reader and Data Writer. I'll go to my securables. I'll search for objects in the database, and I'm going to search for all objects of type, and the type I'm going to choose is just tables. So let's have a look at all the tables. Now, just as an example, what I'll do is we'll just go to the supercar table. And in that supercar table, I am going to allow it to select. Now, what this means is, as of this point in time, the only thing that the web app can do with this database is select rows out of one table. We can go even further. We could go all the way down to column permissions. And then, for example, we could say, I only allow it to select the number of cylinders, the description, the engine capacity, and so on and so forth. Now, I'm not too worried about that for this particular table because it's meant to be read by everyone. But that could be useful for other entities in the database where you may not want everyone reading every column. So I'm going to cancel that, but I am going to say OK to this one, and then I'm going to jump back over to the web app, and I'm going to try an attack here. And this attack is going to be a union-based injection to get all the passwords out of that user profile table. So remember, that one looks just like this. And let's run that. Now, because I'm still allowing these internal errors to bubble up into the web app so that you can see what's going on, we can see the exception here. And we can see that we no longer have select permission on the user profile table. So besides all those other mitigations we've already looked at in this module, this principle of least privilege puts an immediate stop to being able to pull data from that table. Now, of course, you do actually need users to be able to query the user profile table because that's how they log in. But the mitigations to this would include things like using a stored procedure that has execute permissions, because when you do that, you don't need data reader on the whole table. You now have one little programmatic structure, the procedure, and you give the access rights to that. So the stored procedure could compare a password with the one stored in the database, and then return whether authentication has been successful or not, but a user couldn't use an injection attack just to select directly out of the table. Now that is a very fine-grained permissions implementation, but I want to give that as an example of how we can structure the way the application is designed such that we greatly limit the access rights the user has to the underlying database. Now, with that said, let me jump over and point out a few key areas to think about when you're looking at the principle of least privilege. There are a few things that you can think about here, and the first one is whitelists again. So we spoke about whitelists a little bit earlier on when it comes to validating untrusted data from the user. You can also apply whitelist to the permissions on the database, insofar as it's a matter of saying, hey, what should people actually be allowed to access? And when we talk about that allowable access, we can make it very granular, so we can go all the way down to the column level. Database servers like SQL Server do have a huge amount of configurability in this area. I mentioned stored procedures just before as well. So these are a good way of restricting access rights. If you can remove those reader and writer rights, particularly from sensitive tables, and use stored procedures instead, that is a much more secure position to be in. What you do have to be a little bit conscious of though, is that that is at odds to some of the modern movements around using tools like ORMs, because ORMs generate their own SQL, and that generated SQL needs access to select out of these tables. So it'd be very hard to use an ORM to directly query the underlying table and then not have read access to something like the user profile table. But again, this is all about defense in depth. So it's a question of defining what are the right defenses to apply in the right places. You can still have read access to the user profile table if you get all of these other layers of defense correct. And indeed, if you are using an ORM that requires that sort of access rights, at least you know it automatically parameterizes. So the whole thing is a bit of a trade-off. Now, speaking of trade-offs, the last point I'll make here is around using multiple SQL logins. So in the example I just showed you where we removed read access to the user profile table, there may be times where you legitimately require read access to that table, but only via admins. So one way of applying this principle of least privilege in a more granular sort of fashion is to have multiple SQL accounts used for different roles in the system. If you're part of the general public, You can't select from this particular table or insert or update into most tables, but if you come in as an admin, then you connect using a different account, and that account does have the rights you need. So this is really about sandboxing the permissions so that a risk in one part of the app doesn't necessarily bring other parts of the app undone. This is all a really key concept within SQL injection. So do look at how you can apply this principle in conjunction with the other defenses we've looked at in this module. Another key defense here, and this doesn't necessarily stop SQL injection outright, but it does significantly limit the damage that can be done, is network isolation. So let me show you what I mean by that. Let's imagine we have our attacker. The attacker talks to the web app talks to the database. So we've seen this concept many times before. Now, one of the things that we saw earlier on in this course is that the attacker can use an injection vulnerability in this model to actually create their own login. Either that or actually crack the password hashes using that pwd compare function. Either way, the bottom line is it's possible for the attacker to get direct access to the database. Now clearly, once that happens, SQL injection doesn't even matter anymore. They've got direct access to the underlying data anyway, but only if they can access that database directly. So let's do this. Let's roll this back, and instead of the web app talking directly to the database, we're going to drop a firewall in here. So the database sits behind a firewall, and the web app has to communicate through that before it can get access to any underlying data. Now that firewall keeps the database off the publicly facing network segment. The attacker has to go through the firewall. And of course, the firewall is configured in such a way that it will allow the web app in and keep the hacker out. So in this sort of model, this request would be rejected. Simply not going to happen. The question then comes down to what sort of rules are implemented on the firewall to ensure that this actually works. Because at some point, people do actually need to connect directly to the database. They're the people deploying the app or supporting the app. So how does that work? Well, one option is that the database may simply be in a private network segment, the same network segment that those supporting the application are in. Another option is that the firewall whitelists allowable incoming IP addresses. In fact, this is what Microsoft SQL Azure Database Service does. When you get yourself a new database, you have to declare the allowable inbound IPs. So it's not quite in an isolated network segment, but it does certainly put a limitation on who can connect. Now, one other concept that does come up a little bit that I want to touch on is the idea of actually having a service tier in here so that the web app is never actually talking direct to the database. Now, what I mean by service tier is something like a web service-based abstraction where the web application itself is talking to the service, and then the service is the one constructing the SQL queries. Advocates of this model will argue that it's a good design because the web app never has the opportunity to execute a SQL injection attack. It would have to be the service tier, and that's downstream of the web app, and the web app only talks to the service tier via agreed APIs. Now this is true. It certainly does offer a benefit to SQL injection, but it does also add some significant complexity into the app, and I wouldn't recommend going down this path unless the inclusion of the service tier actually offered some other tangible benefits to the app. So maybe it's a great way of abstracting the data tier away and having multiple client interfaces into it. A web app, a mobile app, integration with other internal systems. That might make sense, but purely as a defense, this does get to be a very clunky implementation, and it actually adds parts to the system that can go wrong. So in fact, there are downsides to adding this sort of level of complexity. There has to be an upside beyond just a defense against SQL injection, for which we've already seen many other mitigations. So do be very pragmatic if you're considering this sort of approach. Regardless though, keeping that database off the public net and away from direct access by attackers is a very good practice. One thing that can be a very beneficial defense for SQL injection is using an IDS or a WAF. Let me explain what I mean by that. So first of all, an intrusion detection system or a web application firewall are independent implementations from the app itself. So in fact, they sit in front of the app. Your request must go through the IDS or the WAF in order to get to the web app, and the defense is then implemented at those levels. Now, these do tend to be signature-based, so they understand what a SQL injection attack might look like, and they'll be rejecting any request that might match that pattern. Of course, you do have to be a little bit careful here as well, because you don't want to reject any legitimate requests. But certainly, as they start to learn what's malicious, an IDS or a WAF can be a really good independent layer of defense. The other great thing about these tools is that they can be maintained independently. And what I mean by that is that they can evolve in response to the threat landscape. So SQL injection is just one example of the sort of things these tools can defend against. They can look at other emerging risks, such as newly discovered threats, and implement signatures to defend against those attacks. And all of this is without even touching the app. So it doesn't mean developers are rebuilding things and testing things and deploying things. It's the device in front of the web app which is updated and maintained. Let me give you 3 different examples of the sorts of appliances I'm talking about. A really simple example around intrusion detection would be URL Scan from Microsoft. It's free, it runs in the app so it's easy to deploy, and it looks for known bad patterns around things like SQL injection. Now, URL Scan can simply reject the request and provide this independent layer of defense. But it's a very, very simple little tool. You wouldn't really call it a full-blown intrusion detection system, but it does provide an independent layer of defense from the app itself. A proper web application firewall is something like Barracuda. Now, Barracuda can actually be a physical network appliance that sits in front of the web server. All of the requests go through Barracuda, and it looks for targeted attacks which it knows to be bad. As you can see here on the website, it can also do things like DDoS protection and defense against other advanced attacks. Now, Barracuda can be a physical appliance, can also be a logical appliance. So as we can see a little bit further down the page, it can be applied to things like Microsoft's Azure or Amazon's AWS. It can sit in those cloud environments in front of that web app and provide all the sorts of benefits I've already mentioned, plus a whole heap more. Another evolution of the web application firewall is something like Cloudflare. So Cloudflare is available as an entirely managed cloud service. It can be the first point of contact for website requests, which are then routed through to your site. And as we can see on their website here, Cloudflare security can include defense against everything from SQL injection to distributed denial of services and a whole bunch of other attacks. Now, the neat thing about Cloudflare being a managed service is that it can constantly evolve to protect against emerging threats. And somebody else manages this for you. It's still configurable to a degree, but you're now not the one having to manage your own WAF. Now, Cloudflare actually does a bunch of other neat stuff as well. So things like providing a content distribution network and optimizing web content to make sites perform faster. And they have the luxury of being able to do this because they sit in front of your site. So this is a really, really neat example of what can be done with a WAF. What I will add though, and this applies to everything that we've just looked at in this clip, is that none of these things are a reason not to get the security in the app right. All of the good defenses that I've spoken about in this module are still essential. This doesn't negate any of them. And of course, all of this comes back to this whole principle of defense in depth again. So these sort of appliances or services are fantastic, but they sit there on top of everything else as an additional line of defense. The very last thing I want to talk about in this module is keeping software patched and current. And this is really, really important, not only because newer versions of the product are more secure out of the box, but because they evolve in response to emerging threats. I mentioned Drupal right up the start of this course, and the SQL injection vulnerability they had in 2014 is a perfect example of just how on top of patching you need to be. And in fact, as you can see here, if those sites weren't patched within 7 hours of the announcement of this highly critical SQL injection vulnerability, you had to consider the site compromised. 7 hours, that's all you had. As I said earlier, that's not even a good night's sleep. But this is how fast these vulnerabilities move. Once attackers learn of a risk like this, your stuff has to be patched absolutely as soon as possible. Now, this is an extreme example, but certainly it's very common practice for attackers to be trawling the web looking for products with known vulnerabilities. So a really fast, efficient patch lifecycle is absolutely critical. Another good example, and this one's more about using modern versions of software, is XP Command Shell. Now, we looked at that in the last module around advanced SQL injection attacks. And at the time, I explained that XP Command Shell is regularly used in examples of SQL injection, but often it's not explained that this is off by default. And in fact, as you can see here on Microsoft's own site, it's off by default because it is used by malicious actors. Now, if someone was still running on SQL Server 2000, and even a decade after it was superseded, there were still many sites running on SQL Server 2000, they would not get this benefit. This would still be a risk, and this could make the difference between a single SQL injection risk in a single app versus the entire compromise of the environment behind the firewall because the attacker was able to use XP Command Shell to execute arbitrary commands in the target network. So people who upgraded to SQL Server 2005 got this for free. Now, of course, they could still go and turn it off, and yes, that does happen, but the newer product had a secure by default position. And this is often what happens as software iterates. It gets better and better and better, and it does it implicitly. So keeping software both patched and current is enormously advantageous. Let's summarize the module. And for this one, I'd like to do it diagrammatically because it puts everything in really good perspective. So let's look at it like this. We have an attacker. When the attacker makes a request to the web app, putting it through a WAF or an IDS can be a great first line of defense. If the attack can be stopped before it even hits the downstream app, then that's a great position to be in. Downstream of there, we have the website. And as we just saw in the last clip, the website should be modern and should be patched. Modern web server, modern web software, all up to date. Now within this web app, one of the really critical things we discussed at the start of this module is whitelisting and custom error messages. Custom error messages, of course, being error messages that are tailored for the user and built as part of the app, not the underlying internal exceptions exposing the implementation in the app, particularly when they expose exceptions that bubble up from the database server. Now, with all that being good, the website should be creating parameterized queries, so using inline SQL with parameters, or stored procedures, or object relational mappers. Anything which parameterizes is a good thing. And again, let me reiterate, that is really the heart of SQL injection, getting queries parameterized. Now really, when the web app sends this query off, it should be going through a firewall. You want to try and have your web app isolated from your database server. The web app obviously has to be consumer facing. It's normally going to be in a public network segment. That doesn't mean that your database has to be though. It simply means that the web app has to be able to connect to your database. And that can be through a firewall that keeps everything else out. When that web app does connect through to the database, we want to see a non-privileged account. So this is where we looked at that principle of least privilege, making sure the account the web app uses can do only what it needs and nothing more. And then ultimately, of course, it'll actually be hitting the database, which should also be modern and patched. And you'll get all the nice security features that organically happen with each new release of database management servers, not to mention all the fixes for actual flaws that have come out via patches. The only other thing we discussed that's worth mentioning here, and again it's a bit subjective, is this idea of having a service tier. So an abstraction between the web app and the database, such that the web app is never actually preparing and sending SQL statements itself. Approach that with caution, think about whether it actually makes sense to the broader architecture of the app, and don't get too caught up in the utopian thinking that there needs to be this segmentation in there. So that's the whole picture. Apply as many of these as you can, think about defense in depth, and SQL injection risks will become a thing of the past. In this module, we're going to start to look at how we can evade SQL injection defenses. And this is really going to focus on what sort of patterns of SQL injection are applications looking for, and how can we construct requests such that they don't match those patterns. Now in this module, your understanding of the SQL syntax becomes really important because we're going to get quite creative about the way we reconstruct an attack so that it executes in the same way, but it has a fundamentally different structure. So let's move on and start looking at what I mean by that. The thing about many injection defenses is that they do involve looking for common patterns. So for example, in the last module on defending against attacks, I talked about validating untrusted data, and that involved the application rejecting potentially malicious requests. The thing about this though is that these basic signature definitions can often be circumvented. And as I just mentioned, this will really just come down to creativity with the SQL syntax. So how can we form those same attacks in a different way such that they evade the signature definitions? Let's go and have a look at a few different ways of doing this. I want to start by talking about signatures, because most of what we cover in this module is going to be about how we actually circumvent defenses implemented by signatures. And what we really mean by signatures is defining a pattern of what an attack looks like. So think back to all the attacks we've mounted through this course. There are some pretty common patterns, and certainly those defending web apps understand what many of those patterns look like. Now this may include very specific attack sequences, and we'll look at some of those in a moment, or it could come down to a more generic pattern match. There's really no one single way of implementing this, but the important thing to understand for this module is that the sort of signatures we're going to look at evading are the ones that are normally pretty explicit about what they know to be bad. Now this is that blacklist approach, and if you recall from the last module, when I talked about validating untrusted data from the user, I was really explicit about using whitelists and not blacklists. So in this module, we're going to see the problem that occurs when an application is just looking for certain patterns that it thinks are bad, because we're going to create some patterns that the app probably doesn't know are bad. Now these signatures are often implemented at various points of the application. So as we saw in the last module, they may be implemented when the website is actually validating the untrusted data. So that's built by the developer and it's in code. But as we also saw in the last module, there could be something like an IDS or a WAF in front of the website, a dedicated security appliance. So it can be something much more sophisticated and upstream of the web app. Now when you do get more sophisticated, some of these appliances can look at more advanced aspects of the traffic attributes. So what if it sees certain patterns from a certain IP? Or what if it sees them across IP addresses? What does good traffic look like? And conversely, what does bad traffic look like? And that's about much more than just looking at a single request in isolation. So although we're going to look at some great evasion techniques in this module, just be conscious that sophisticated devices go well beyond just looking at the sort of patterns we're going to see here. But with that said, let's move on and start looking at some basic evasion techniques. Let's start with something really straightforward. We know that this syntax is enormously prevalent. So remember, this was the tautology, closing off a string and then using a statement that's always true. So the 1 equals 1 syntax is enormously prevalent. Now, there are some less prevalent alternatives that mean the same thing. And again, keep in mind the whole definition of a tautology is just to try and have a statement that's always true. So for example, this would always be true. It's a perfectly valid tautology. We're just matching two strings now instead. Or another example would be this one. 2 is always going to be greater than 1. That's always going to be true. But if the app is just looking for the or 1 equals 1 syntax, then this one will get through. Even a syntax like this is still accurate. It's syntactically correct because we have more characters after the F on the left-hand side of this equivalency. It's going to equate to true. So foo is actually greater than F. And this is the sort of thing that's often not looked for in signatures for defending against injection attacks. What you'll often find when trying these different attacks is that it's going to take a lot of probing. So you'll need to figure out what sort of patterns are rejected by the web app versus which ones are accepted. So this is very much a trial and error approach because so many web apps are implemented in different ways. That said, you'll also find that there are some known vulnerabilities within certain devices like WAFs and IDSs. So if you can identify what the device is that's actually protecting the app, you may well be able to find known risks within there that can be circumvented by some of these evasion techniques. So that's basic evasion. Let's go on and look at encoding. Encoding can be a great way of evading SQL injection defenses because it can take characters and represent them in an entirely different form whilst actually not losing the actual intent of the character. So for signatures that are looking for very specific patterns, this can be a great implementation. Now you can use a number of different encoding patterns to circumvent this sort of defense. And the pattern you use will depend on both the context of where you inject the attack and the ability of the application to then decode that attack. So for example, something like URL encoding can be very useful at getting around a signature-based defense. But of course that URL does have to be decoded by the system. And it's the same with using something like hex. And in fact, we'll see an example of using hex a little bit later on in this module. UTF-8 or Unicode is another way of encoding for evasion, and even using something like SQL's char function. Because if we pass an ASCII value in the char function, the database will kindly resolve that to a character that can be part of an injection attack once it hits the database. Now the web app, or the device in front of the web app, is often not looking for these encoding patterns. So encoding before the attack is passed in the request can be a very effective mechanism of evasion. So that's encoding. And again, lots of different ways depending on the context you're using. Let's now go and have a look at how we can still use the original attack strings, but we'll just split them up a bit. Splitting strings is a really easy way of changing the pattern of the attack such that it doesn't match what the app might be looking for as a potential attack. So often what's happening is the signature is trying to make an exact match to the attack payload that's passed to the web app. So if you can split that string up, that can be a viable means of avoiding detection. A really simple example of what I mean by that is something like this. So in this attack, we're using SQL's exec function so that we can pass a string to it, and then when this runs, the database server will simply evaluate the string and execute it. So we can clearly see that this is still select password from user profile, but obviously what I've done here is I've split both the select keyword and the from keyword. So if there's any sort of signature pattern matching going on that's looking for either a select word or a from word, this is going to circumvent that. The fact that SQL Server will join these strings together and evaluate it as one query is inconsequential because upstream of there is where the signatures are. And the signatures are not going to find a select or a from. So unless the pattern matching is sophisticated enough to understand what's going on here, this is going to get through the filter. So splitting strings is a very, very common evasion technique. Let's go and look at another very common evasion technique, which is using diversity in the whitespace characters. Whitespace diversity is a pretty common way of evading SQL injection defenses. And really what we're talking about here is how can we replace something like a space, which the signature is looking for, and change it to something else which the signature is not looking for. Now this works because often signatures are looking for multiple words together. So for example, if a signature was just looking for, say, the word select, you'd end up with a lot of false positives. Select is a perfectly valid string that's often going to be sent to the web server as untrusted data. For example, it might just appear in a sentence somewhere. Just matching this one word could lead to a huge number of false positives being generated. A better match for an injection attack might be something like a union select. So we've seen this syntax used already in our union-based injection, and looking for this sort of string is far more likely to reduce those false positives. But here's the catch when it comes to white space diversity. What do we have between those two words? And more specifically, what is the signature looking for? So, for example, is the signature just looking for a single space? If we were to put multiple spaces between the words union and select, that would still be a syntactically correct piece of SQL. There's no limit on how many spaces you put there. It will still execute. It's perfectly valid. But if the signature is only looking for union, single space, select, multiple spaces would circumvent that. Another option might be tabs. Is the signature actually looking for the presence of a tab between union and select? Again, that's still a perfectly valid piece of SQL syntax. And a tab could be encoded and passed to the web app, where it then filters down into SQL Server and is treated as a tab in the database server. But does the signature know to look for it? Same again with line returns. You can have as many line returns as you like anywhere within the SQL statement, and it's still perfectly valid. But does the signature know to look for it? So these are all the sorts of things that you want to test when you're looking for what the signature knows to be bad versus what you can possibly slip through because it just simply wasn't sophisticated enough to catch it. So that's white space diversity. And that again is another very common mechanism of breaking up the pattern of an injection attack. Let's go and have a look at another very popular one, which is the use of inline comments. We've already looked at what comment syntax looks like in SQL, and certainly there are very valid reasons why it's used. Comments within code is a perfectly legitimate pattern when developers are building software. But as we've also seen, we can use comments in SQL injection attacks, and so far we've used them to comment out other pieces of the original statement that we didn't want to execute. But we can also use them to obfuscate the payload of an attack. So we can actually split up that payload by using the comment syntax such that it helps us avoid signature detection. So for example, have a look at this pattern. Now this is perfectly valid, and what you can see here is that we've just got open comment, close comment syntax all the way through this statement. Now nothing is actually being commented, because the comment opens and then closes again immediately, and then there's another valid piece of SQL after that. But this would still equate to a perfectly valid tautology. You can take this, throw it at the database server, and it will still check that 1 does indeed equal 1. So that's one way of using comments. Another option is to actually look at splitting the comment across multiple parameters. So what I mean by that is imagine that we have a username parameter, and we enter this value in the username field of a website. So single quote or 1, and then we start the comment. Then we go down to the password field and we do this. We close the comment equals 1 dash dash. Now, if the application then concatenates these parameters like this, we have the potential for a SQL injection attack. Of course, we are working on the assumption that there is going to be a SQL statement concatenated and consequently have the risk of an injection attack, and that the username is going to appear before the password, because the order doesn't matter. The SQL syntax could well be checking for password and then checking for username. So again, this is one of those things that requires a little bit of probing to try and figure out what the web app is doing. But certainly using inline comments is a great way of obfuscating the attack payload such that it circumvents this signature matching. So that's comments. Let's move on and have a look at how we can use variables to also circumvent matching. Variables are another very viable way of circumventing the common patterns that an application might be looking for. And the thing about variables is that they're a great way of actually breaking the statement up. So rather than just having this one line of SQL, instead assigning it to a variable and then executing the variable. Now when we do that, we can also assign a hex value to the variable. So by using hex, we can avoid the use of quotes. And inevitably, quotes are one of the patterns that commonly appear in signatures. And in fact, we've seen ourselves throughout this course, we've used quotes extensively as part of our injection attacks. Now, imagine a pattern like this. So we've seen this syntax. We used it to discover the version of the underlying database. This is a pretty predictable pattern, particularly the select syntax, as well as the @@. We know that @@ often signifies a system command. So instead of using this sort of syntax, what if we used a syntax like this? So this is just the hex encoding of select @@ version. And by declaring it to a variable and then executing it, we're avoiding the common patterns that are expressed in the original query. So this is a good example of actually combining two different things we've now discussed in this module. One of them being encoding, which is the hex, and the other one being the variables. So by using this approach, we can potentially sneak past SQL injection signatures that are looking for that earlier very predictable statement. So that's variables with hex. Let's move on and look at one more approach, which is string manipulation. We've already looked at a bunch of different ways of obfuscating the SQL injection payload. What I want to look at now is a couple of other ways that we could actually manipulate that original source string such that it doesn't match any sort of patterns you might find in signatures. So think about the different ways in SQL that you could manipulate and transform those queries such that they pass the signatures but are then restored and executed as a valid query. So for example, what about reversing the string? What if we did something like this? So you can see on the line that begins with set there, we're using the reverse command. And if we read this backwards, we can see it says select password from user profile. Now that string is obviously reversed. The reversed function will re-reverse that string, and then the exec command will simply execute it. So any sort of pattern that's looking for select or from or anything like that is not going to identify this, not unless the pattern itself is smart enough to identify when the string is reversed. Another way we could go about this is concatenating the string. So we can actually join the whole thing up like this. Now this looks very messy, so let me explain what's going on here. We're declaring two variables, x and y, they're both varchar 80s. X is the actual SQL injection attack, and if you ignore all the lowercase x's in that variable, you can see that again it says select password from user profile, and then y is a simple concatenation of the actual injection in that line. So in fact we're concatening 6 separate substrings, and each one of these substrings is just selecting out the piece of the SQL query. So again, any sort of signatures that are looking for keywords like select or from or any sort of pattern that might normally adhere to are not going to identify it in this particular string. Not unless it's intelligent enough to realize the actual semantic nature of the query. The fact that SQL Server will break this string down and extract a command, which is a SQL injection attack. So any sort of signature-based defense would have to be quite sophisticated to actually pick this attack up. And really that's been the story of everything we've looked at in this module. If there's sufficient sophistication to understand the implied intent of the injection payload, then the request could be rejected. But all of these do require much more than just simple pattern matching. They require some real smarts in what is inevitably a device sitting in front of the web app. Because certainly just untrusted user validation is not going to realize that most of the evasion techniques that we've looked at in this module are actually SQL injection attacks. Let's summarize the module. And clearly, the story here is that manipulating what would otherwise be a pretty common injection attack pattern can circumvent the actual matching based on signatures. And that's what all of this has been about. Just trying to make sure that we can represent our attack in a way that the application, or a device sitting in front of the application, can't recognize. So that could mean a bunch of different things. Encoding, splitting, white spaces, comments, variables, and string manipulation. And sometimes a combination of a few of these. So we saw that when we encoded to hex and then we passed it as a variable. But really the key message from this module is that signatures alone just aren't enough. Signatures can be defeated. Certainly signatures that are doing simple pattern matching, because it's just so easy to break away from the pattern. And yes, some devices do get a lot smarter and they look well beyond just the pattern of the individual request itself. But really the underlying message here is that if there is a SQL injection risk in the actual code of the app, there are many ways to evade simple defenses that are nothing more than signature based. So for you as an ethical hacker, this provides a bunch of different ways of still exploiting that risk. And for those wearing a developer hat, it shows just how important all those defenses that we looked at in the last module are, and why defense in depth is absolutely critical when it comes to SQL injection. In the final module of this course, we're going to take a bunch of stuff we've learned throughout the previous modules and just simply automate it. So it's great that we've gone through and we now understand the actual mechanics of how these injection attacks work, but they can be very laborious. They're a lot of hard work, and they're the sort of work that we can automate with good tools. So in this module, I want to show you a few different classes of SQL injection tools, and then how they can help you in your analysis of sites as an ethical hacker. Let's take a look at what's coming up. So firstly, as you've seen throughout the previous modules, injection attacks can be hard work. They do get laborious, they do get repetitive. So particularly think back to when we were doing things like the blind injection, and we needed to work through character by character, row by row, table by table. That can be a lot of hard work. The thing is though, repetition is actually great for automation. Software is very good at simply repeating processes. And when you think back to some of the attacks we did, particularly that blind attack, it really was just a repeatable, predictable process. And that's exactly the sort of thing that these automated tools can do for you. So we're going to take a look at a bunch of different classes of automation. Some of them are quite rudimentary, yet can be effective. Others get very advanced, and they all range from free through to full-blown commercial editions. But I want to pick a good range of tools demonstrating very different approaches to the process of SQL injection automation. Now, also when we look at this, you'll see that some of these tools just simply help with discovery. So they make it easy to find where there might be an injection risk, after which you've got to go and do all the sorts of hard work that we've seen already throughout this course. However, some other tools will go all the way through to full exploit. So we'll look at a couple of tools in particular that will exfiltrate data out of the system using injection risks. So we're going to see a really good range of tools here that should make your job as an ethical hacker much easier when it comes to identifying SQL injection risks. I want to start looking at automation by starting in the browser. And obviously this time we're in Firefox. And I'm in Firefox because there's an add-on here called SQL Inject Me. Now, browser add-ons are a very particular type of automation. They generally tend to be pretty rudimentary, but they also generally tend to be free, and you often see them feature in very basic opportunistic SQL injection attacks. So think about the sort of things that you see from hacktivists or mischievous kids, and coincidentally they're often the same thing. But I digress. Getting back into browser add-ons. And I want to show you how it works and why there's an add-on within the browser. So I'm going to jump over to the Supercar Showdown page here, and I'm going to jump into the menu, Tools, SQL Inject Me, Open SQL Inject Me sidebar. Now you'll see that there are a couple of forms here. There's a logout form, and this is actually a form on the page with an ID of logout form. And there's another form called Unnamed Form 1. And this is actually the form behind the search page. Now I'm presently logged in. What I want to do now is go over to my account and then drop down into Change Password. Now when we get into there, we can see that there's also a form called Unnamed Form 2. And when we open that up, we'll see that there are a number of fields here on the left-hand side of the page. And what I want to do here is check each one that I want to run a SQL injection test against. And in fact, if we drop this down and take a look in one of these, we'll see a whole bunch of very typical injection looking patterns. So there are a few tautologies here We can see some union-based injection as well. And then there are some encoded attack patterns. So all of this is inevitably pretty familiar to you by this point in the course. Now what I'm going to do is just drop that menu back down and then just simply execute. Now I've got a little prompt that's appeared over here on another screen, and it's simply going through and running tests against each one of these fields. So it's testing those patterns against those fields when the form is submitted. And here we now have a report. And what we're actually seeing here is that some of these results have turned up in red. And in fact, the results in red are giving us an HTTP status code, and they're giving us the value tested. Now, if we scroll down a little bit, we'll also see that some results actually come up in green. And effectively, what the report is telling us is that some of these strings that it has posted in the form values may indicate that there is a risk of SQL injection. Now, the really important thing here is that this tool is very much about discovery as opposed to exploitation. So this is not going to get data out of the system. You'll still need to go and actually manually execute those attacks. But this sort of testing can be very useful for identifying where you should start with those attacks. And what we're really looking at here is a fuzz test, or in other words, a test where we're throwing these typical patterns at various form fields and we're just seeing what the results are, particularly as they differ from the norm. So what sort of patterns might cause us to get a result which is not consistent with the result under normal usage? However, this is really a very rudimentary way of doing fuzz testing. Let's move on and have a look at a more advanced approach to fuzz testing using Burp Suite. We just touched briefly on fuzz testing in the last clip, and inevitably the SQL Injector browser plugin of Firefox was doing a very rudimentary version of that. Let's take a moment though and define what I'm talking about with fuzz testing. And really it's all about using automation to take, as the definition here says, invalid, unexpected or random data and throw it into the inputs of a system. So in the case we just saw, that was SQL injection style attacks thrown into form fields. Let's take just a moment to have a look at some of the typical payloads that you might use when fuzz testing for SQL injection risks. What you're looking at here comes from the FuzzDB project over on Google Code, and inevitably a lot of this should now be familiar to you. So you'll see a bunch of tautologies, everything from the very classic 1 = 1 through to other equivalencies using letters or less common patterns. So think about the previous module on evasion techniques. A good robust set of fuzz testing logic is going to include all sorts of values that may actually be the ones that slip through SQL injection defenses. So beyond just the tautologies, we're also seeing a bunch of union style attacks. We can see hex encoded attacks. And of course we can see some SQL injection keywords and system commands. And in total we're looking at 143 different possible strings here. It's certainly not exhaustive, but that's a reasonable range for us to use in this next automation example. So I've got a copy of all these on the clipboard. And what I want to do now is jump over and show you Burp Suite. Just before I do that though, I want to jump back to the vulnerable website and make a quick request. Okay, so here we are back on the vulnerable website. I'm going to scroll down to the cylinder layouts where we've spent so much of our time testing SQL injection in this course. Now here's what I'm going to do. I'm going to hit the link to the 4 V12 cylinder layouts, and what you'll notice is that the website is just sitting here, not responding. Now there's nothing wrong with the site, but what I've done is set up my browser to proxy through Burp. And what that means is that Burp has intercepted this request and it's now waiting for me to take some action. So let me now jump into Burp. So this is Burp and I'm using the free edition here. There is a commercial edition as well. And the thing about Burp is it makes it very easy to proxy your browser traffic, intercept the request, manipulate it, and then fuzz test the resource that that request was being sent to. Now we can see the proxy tab up the top here has gone orange. So let's jump into that. And then here we can see the request that we just issued from the browser. So in fact, you can see here that it's a GET request. And of course, it's going to cars by cylinders with the query string parameter of cylinders equals v12. Now we've also got all the other request headers here. And what Burp has done is highlighted every section here which it thinks might be suitable for some fuzz testing. So effectively, it's all the input parameters, so v12 on the cylinders value, and it's all the cookie values as well. Now here's what I'm going to do. I'm going to jump over to Action, and I'm going to send to Intruder. Now when we do that, the Intruder tab goes orange. I'm going to jump over to Intruder. We can see the host represented here and the fact that we're talking to it over port 80. I'm going to go to Positions, and what we see now is every one of those pieces of untrusted data being highlighted in orange. So remember, we defined untrusted user data earlier on in the course, and it's basically anything that an attacker can manipulate and submit back to the site. Now that's exactly what we're going to do here. But what I want to do first is clear all these other payload markers, because the only thing I actually want to test is the cylinders. So let's clear that. I'm going to select v12, and then I'm going to add it. So now we've only got the one marker, it's just v12. Now I'm going to jump over to the Payloads tab because we need to define what it is that we're going to fuzz test that parameter with. Now I've got all of those 143 fuzz testing SQL injection patterns we saw just before on my clipboard. So I'm just going to paste those in here to the payload. And what I'm going to do now is jump up here to Intruder and start the attack. I'm getting a little warning here about the free version. It is going to be time throttled, as well as having some other functionality disabled. So clearly there's a bit of an upsell here to the professional version. But this is fine for now. I'm going to say OK to that. And then I'm going to maximize this window here. Now we'll see one request here with a comment of baseline request. So this is just a request exactly as I issued it from the browser. We can see that it has an HTTP 200 status, and it's got a length of about 5,700 bytes. We can also see a number of other requests now appearing, and effectively each one of these requests is a test for the pattern that we saw before on the fuzz test slide. And we can see that these tests are now returning sometimes different status codes and sometimes different lengths. Down the bottom left-hand corner of the page, we can see the progress. So we can see the full 143 tests there still ongoing. Here's what I want to do though. I want to have a look at just a couple of specific requests, and in particular at the responses. So I'm just going to pause this attack for now because I'm just going to use the first few results to demonstrate what we've actually gotten out of this process. And I'm going to start by looking at this first request here, at least the first one after the baseline request. Now when I select this request, we can see some tabs below, and it's defaulted to the request and to the raw request. And this is basically just what we saw before, the only difference being that the cylinders parameter has now got that SQL injection attack in it. So this is the pattern that we are fuzzing in this request. Now if we go and take a look at the params tab, we'll see that represented a little bit more clearly. So all the cookies are the cookies from before, but there's this URL value which is our SQL injection test. What I really want to look at now though is the response, because I'm a little bit interested as to why this response is only just under 4K. So that's actually quite a bit smaller than our baseline request. And really this is the whole point of fuzz testing, trying to see which requests are causing the page to behave differently. So what I mean by differently is things like a status that isn't 200 or a response length that's very different to the original one. So the response defaults to the raw response, but for the sake of legibility, let's jump over to the render response because this is going to show us what the actual web page looks like. And if we scroll down a little bit here, we'll actually see that this is the entire page. There's no CSS or nice styling, but we can clearly see our attack pattern repeated at the top of the page. So remember, this is where you'd normally see something like V12 engine layouts, and then that's it. So basically what's happened here is that there hasn't been a successful SQL injection attack. The underlying database query has returned no results, and the page is just reflecting the input. I'm a little bit more interested in this second request though, because we can see that that has an HTTP 500 response and quite a large response body. And if I click on this, we can see that the render is now actually reporting a server error. So this is effectively confirmed error-based SQL injection, in part because we can see it's an internal exception, and in part because the exception details do actually disclose that it is a SQL exception type. So this result here says to me, this is something that we want to investigate further. So that's a good fuzz test result. Let's pick one more example, because down here on request number 6, we're getting an HTTP 200, but we're also getting a response size that's sort of partway between our baseline request and the exception we just saw on the 500 response. Let's have a look at this one. Now I'm going to slowly scroll through these results. And what we're actually seeing here is the Agera R, the GTR, the Wayera, LaFerrari, and in fact, if we keep going, we'll see we've got all 10 results. So what this is telling us is that the SQL injection payload, which we can clearly see is a tautology, is returning all 10 vehicles, not just the 4 V12s. So this is confirmation that it has found a valid SQL injection attack. Now, of course, you still need to go and do something with this. This isn't actually getting data out of the system. It's enough to confirm there's a risk, but it's always nice when you can actually demonstrate the exfiltration of data. So to do that, let's move on and take a look at Havage. So we're now looking at Havage, and Havage is a GUI-based SQL injection tool that will actually exfiltrate data. Now it comes in a couple of versions, the free one that we're looking at here, as well as a commercial version. Or at least it did come in a couple of versions, because at the time of recording, the website that you see here appears to have disappeared. You can still go and download this from various places across the web though. But I wanted to include Havage in this course anyway, because it appears very, very frequently as a means of SQL injection. Now, one of the reasons it's so popular is that it is GUI based. It's extremely simple to use. In fact, it's so simple that you'll often see it being the tool of choice for hackers that really do not have any idea about SQL injection. In fact, if you go and have a look at some of the YouTube tutorials, you'll work out pretty quickly that it's very popular with kids. Rightly or wrongly, it is a very common tool, and I want to give you a quick overview of how it works. So what I've done is in the target field here, I've put in the URL of the page that we've been using so frequently throughout this course. And I'm just going to go up and hit the Analyze button here. Now, of course, Havage is simply making HTTP requests to look for SQL injection risks. And as we'll see down here in the bottom left-hand corner, it has found a database name of hackyourselffirst_DB. That is the internal database name of our system. Now I'm going to jump over to the Tables button here, and I'm going to ask it to get the tables in this database. So it's going to go through and just automate the process of forming the right requests with SQL injection payloads and looking at the responses. It's found a bunch of tables. Let's go and check user profile, and we'll now go and get columns. Now down the bottom, you'll actually see some of the requests that it's issuing, and you'll see things like selecting from sys objects. So we've gone through this when we looked at the underlying mechanics of an injection attack, and we know that these system tables will disclose the internal structure of the database. And clearly we now have a bunch of columns in the user profile table. Let's go and get the email address, let's get the password, and let's now get the data. And what you're now seeing is the internal data exfiltrated out and displayed here in the Havage UI. This clearly is an extremely simple attack, and I wanted to demonstrate it here because I think that frankly this is about the best possible representation of just how easy a SQL injection risk can be to exploit. This is one of the things that keeps it in that #1 risk position on the OWASP top 10. And clearly the sort of data you see here could actually be very impactful as well, which was the other attribute that kept it right up the top. So that's data exfiltration with Havage. It's extremely basic, and that's really the point. Let's now move on and have a look at a more sophisticated tool for data exfiltration, and that's SQL Map. When it comes to actually extracting data from the database, few tools compare to SQL Map. It is the canonical SQL injection tool, and it's extremely powerful. It's also open source and entirely free, which probably partly accounts for its popularity. But it is actually a really powerful system, and you can get a bit of an idea about just how extensive its features are by taking a quick look at the usage page. Now, I'm not going to scroll all the way through this, but you should get a sense based on the size of the scroll bar just how comprehensive this tool actually is. It's excellent for basic attacks like an error-based attack or a union-based attack, but it's also very good at doing blind injection, both Boolean and time-based. So it is an enormously powerful tool. It's also all command line based, so it's not quite as trivial as something like Havage, but it does make it much more powerful for those who understand the command syntax. Let's drop over to a command window and have a look at how it works. I'm just going to run a very simple command this time. So I'm going to call SQL Map, which is built in Python. I'm going to pass the URL that I want to attack, and in this case it's the same URL that we've been using so often through this course, the same one we just used for Havage as well actually. And I'm going to pass a schema switch. So I just want to extract the schema. Now as we start running this, SQL Map is going to do a very similar thing to Havage insofar as it's just simply issuing HTTP requests and looking at the response. Now these tools are particularly adept at actually forming the request in such a way that it can extract data from the response. So for example, it will exploit error-based SQL injection risks such that the internal error is returned in a way that it can actually extract the specific data from the error. Because remember, the response from the web server is going to be an HTML page, even when it's error-based injection. And we rely on tools like this to be able to actually extract the relevant data. So this has just finished running. Let's have a scroll through and see what it's found. And in fact, we can see the last few tables here already on the page. As we scroll up, we'll see each table in the system, and some of these we're now quite familiar with, and we'll see each of the columns in the system, including the data type. So for example, here we can see the supercar table, and we know already that there are columns such as cylinders and power kW, top speed km. We've seen these throughout the course. SQL Map has just been able to go and discover all this very, very quickly by entirely automating the injection attack. So if you're looking for a tool to both probe for risks and then actually exfiltrate data out of the system, it's very hard to go past SQL Map. Now tools such as SQL Map and Havage and that SQL Injector browser plugin are dedicated SQL injection tools. Burp Suite is a bit broader than that, but most of these do have a focus on that one risk. Let's now move on and have a look at a much more comprehensive means of testing not just for SQL injection risks, but other risks in the system. And we're going to do that by using NetSparker for dynamic analysis. So this is NetSparker, and it's a dedicated dynamic analysis security assessment tool. So by dynamic analysis, I mean that it's going to run against a live running website. And in fact, you can see that I've already got the target website in there. Now, I'm not passing in any particular path that I think might be at risk of SQL injection. I've simply given it the root of the website. There's a bunch of configurability here around what sort of test we actually want to run, but I'm just going to leave everything default. And what that means is that NetSparker is going to look for a whole range of different risks. Now, it is a commercial product. You do pay for the privilege, but it's a great point and shoot sort of tool, and you'll see just how comprehensive the results are after this scan runs. But before I actually run it, I want to do one more thing. I'm going to jump down into authentication and into form authentication, because this is a website where you log in, and there will be risks hidden behind the login. And what you really want to do when you're looking for SQL injection risks is make sure you look everywhere. Just because a particular feature of a site might be behind a login doesn't mean it's okay to have injection risks, or any other risks for that matter. So it's really important to assess those authenticated pages as well. Now, I've already entered my credentials in here, and these are just the form credentials of the Hack Yourself First website. It's exactly what I would enter into the website when I log in. Plus, you can also see I've got the URL of the login form up here as well. And this is really all we need. Now, what I want to do is just verify this login and log out. Now, I've previously verified it, which is why I've got the tick next to the button here, but I want to check this again. And what NetSparker is now going to do is try and log in on the left and then show me a log out view on the right. And I'm going to validate that this is correct. And it's simply to make sure that NetSparker does know how to authenticate to the website and what it looks like when we're authenticated versus not authenticated. Now on the left, we should see this login simulation. So what it looks like when we're actually authenticated. I'm going to hit the little menu icon here and I can see that it says hello Troy, so I must be authenticated. Now on the right, this should be our logged out state. So let's close the modal, hit the menu again, and I've got a log in link. So this checks out. Left is logged in, right is logged out. We've now verified that NetSparker knows how to log into the website. So I'm going to say OK to that, and I'm going to hit the Start Scan button. Now this is a very comprehensive test. It's going to run for quite some time. And what we'll see down the bottom left-hand corner of the screen is the current progress. And it's going to go through and make many thousands of requests. And as these requests are being made, we'll see the sitemap being built up in the top left of the screen, and we'll see all of the results appearing to the right of the screen. So a categorization of risks and then individual issues down beneath that. This is going to take a long time to run, so I'm going to leave it going and then we'll come back to it once it finishes and have a look at what it's found. Okay, so the scan has just wrapped up. And per the scan information down here on the bottom left-hand corner, one of the big things we can see here is the total number of requests. So that's over 15,000 requests that NetSparker has made to this website over the course of almost an hour and a half. So it's a very comprehensive set of tests. Now on the top left here, we can also see a sitemap. And what NetSparker has done is just built up a logical map of what is actually on the website. So we can see the paths that it's found here and the resources it's found, as well as some messages about certain things we might want to take a look at security-wise. Now before I start looking at the results though, I want to flick over to the browser and show you what the site now looks like. So here's the site. If we scroll down a little bit, we'll see that we've got a lot of votes in the system. In fact, we've got 290 votes for Pagani. And if we drill down and actually have a look at these Paganis, and look at the way error, and then scroll down to our comments, we'll see that there's an awful lot of content in here that looks like a SQL injection attack. Now this is really important and it's something to remember with dynamic analysis tools. In order to test for risks, they need to submit data to the server. Now that can play havoc with your live data, so you've got to be really cautious about where you run tools of this class. They're often better off being run in a staging environment or a test environment, somewhere where it doesn't matter if the data gets corrupted in this fashion. Now we're not necessarily seeing this data because of a SQL injection risk. Rather, this data was used to probe for SQL injection risks. But of course, that does beg the question, what risks did NetSparker actually find? Let's jump back over and take a look. So looking at the issues section here in the NetSparker report, I obviously want to focus on the SQL injection ones. And you'll see 3 different classes of injection here. So let's take a look at this one first. And what we'll find here is a number of different paths where SQL injection was found. So it was found in the Vote API. We saw that one during the course. It was also found in Cars by Cylinder, and we saw that many times. And then we can also see it was found in Makes and Leaderboard. Again, we also saw injection there. So this has effectively automatically confirmed what we have found. Now I want to give us a little bit more room up the top here and have a look at the information that NetSparker gives us about this risk. And one of the reasons I really like NetSparker as a tool is that it's very easy to consume this information. What you need to consider as an ethical hacker is that once you do find vulnerabilities in a system, how are you going to communicate those? Inevitably, it's going to be a developer that needs to get this information and fix the underlying risk. So it's really important that they get easily consumable information. So what I like about NetSparker's approach is that it's very easy just to go and see the risk in action. We'll just check this URL out. And here we can see that underlying SQL exception being exposed. Now while we're here, note that NetSparker is using exactly the same approach as we've looked at throughout this course, which is by trying to convert something that is not an integer to a data type of int. So as clever as tools like this are, they're not doing anything that you don't know already. It's just that you've had to learn the underlying mechanics throughout this course. Let's jump back over to NetSparker. And the other thing I like here is the classifications. So we get data that puts it in the context of things like PCI, the payment card industry, or OWASP, and I've talked about OWASP already. Again, all of this is really nice, easily consumable information. Now, as well as this first SQL injection finding, it's also found blind SQL injection on the same paths, which you'd expect if it's already confirmed error-based SQL injection. And if we have a look at an example like Supercar Leaderboard, we can see from the URL that it's actually using a time-based blind injection attack here. So there's the wait for delay syntax that we manually implemented in the blind SQL injection module. So again, this should be very familiar. It's just automated. So this is really neat. The fact that we've just given NetSparker a URL and all of that hard work that we've manually gone and done throughout this course is simply automated away. It's not just SQL injection either. When we look back at the scan results, we can see that there were a bunch of critical ones, and clearly SQL injection are the critical ones. But we also have vulnerabilities by other classifications as well. Important, medium, even some low and information ones. And as we scroll through, we can see that there are different types of risk here. Cookies not secure, passwords over HTTP, cross-site scripting being another big one from the OWASP top 10. We're not going to go through those in this course, but the important point I want to make here is that a dynamic analysis tool like NetSparker is exceptionally good at finding all of these risks which are discoverable simply by issuing the right request patterns. So a product like this is a great thing to have in your arsenal of testing tools. Let's summarize the module. And obviously the key thing to come out of this is that automation can be enormously powerful. Throughout this course, we've seen how laborious it can be to actually exploit SQL injection. So being able to just simply point a tool at it and let it go and identify risks, if not actually also do the data extraction, is a very efficient way of working. Now this is a great place to start. So something like Burp Suite doing fuzz testing, for example. But of course your work doesn't end there. You do have to go through and actually verify that there is an underlying risk, because automated tools don't always get it right. There are times where they have false positives. And of course, in your capacity as an ethical hacker, there's inevitably going to be some follow-up work once you do identify this risk. The other thing about these tools is that they're a really neat way of learning about injection. So have a look at the sort of attack patterns that they use, either the ones that they show you in the UI, or even proxy those tools through something like Fiddler and have a look at how it's actually forming the request. You can learn a lot by looking at how these tools automate the process. But the final thing I'll say about automation, and indeed about this entire course, is that nothing beats actually understanding what's going on. Clearly, it's very easy to use tools like this, especially ones like Havage, to just point them at a website and let them fire away. And as I said in this module, there's no shortage of children going out there and running them against live websites. But by this point in the course, you actually understand those underlying mechanics of how the SQL injection attacks work. You know how to identify sites that are at risk, and you know what patterns are required to mitigate those risks. So this is a great way to end the course, with you not only being able to automate your workflow and work much more efficiently, but to also understand what it's actually doing.